Hey everyone, Professor Dustin here, and I'm going to talk about particles and systems in this video. So recall what we're doing in physics is trying to find a mathematical abstraction for the real world. We're going to use this mathematical abstraction to do calculations, make predictions, and then in principle we could go into the lab and check to make sure those predictions are accurate. But when we make an abstraction of the real world, the first thing we have to do is we have to take objects in the real world, which could be extremely complicated, and replace them with point masses. So these are points which have mass but have zero size and definite locations in space. It has a single location in space rather than an extended object which has multiple locations. We're also going to call these things particles. So particles and point masses are exchangeable terms. Don't get confused. There are particles in physics, fundamental particles. They're electrons and protons and quarks. That's not what I'm talking about. That's a different concept. What I'm saying is the objects that we're going to replace real life objects with point masses, we're also going to call them particles. So if you have a collection of these point masses or particles, you have a system. So that's just a way of specifying the things in my system are the things that I'm going to worry about. Things outside my system I am not going to worry about. So I've drawn on the whiteboard a series of dots, black and blue. The intention is that these dots represent objects which I've abstracted out to be points. The black points I want to be inside my system, and the blue points I want to be outside my system. So what I'm going to do to define what my system is, I'm just going to draw a dotted line around all the black points. So now everything inside the red circle is in my system. I'm going to call that internal. And everything that's outside that dotted red line is going to be external. So now I have a system, I have things that are internal to my system, and I have things which are external to my system. Okay, so the next level of abstraction that we've been dealing with is once we have objects, we can have objects interacting with each other. And we've only so far dealt with momentum transfer between objects. So this is like if two objects are touching, they can transfer momentum. If two objects are far away from each other and there's a long distance interaction like gravitational interaction or the electromagnetic interaction, they can interact with each other as well, but they transfer momentum. That's what interactions do. Well, so now that we have an internal system and an external system, we can talk about three different kinds of interactions. We can have an interaction between two external objects, so that's two objects which are both outside of our system. We can have internal interactions, that's interactions which are between two internal objects. And then of course we can have interactions across the boundary, which are interactions between an internal and an external object. Okay, so the first thing we want to do is we want to be clear that we can ignore all the interactions that happen outside the system. Those things don't touch our system at all, and if we don't care about anything but inside our system will not be influenced by those. Okay, fine. So we do have these interactions which are across the boundary of our system between internal and external interactions. So let's first make an assumption that those aren't there. So if we've picked a system such that those kinds of interactions don't exist. So if we assume that there are no internal to external interactions, that therefore there's no momentum transfer across the boundary, we can say something very powerful about this system. So we can say that the total momentum of this system is conserved. So if there's no internal to external interactions, no interactions which transfer momentum across the boundary of the system, then the total momentum is conserved. So if I write the momentum as a sum of the individual momentum of the system, P1 plus P2 plus however many we have, maybe you want to write that as M1V1 plus M2V2. The word conserved means that this total momentum right here is constant. That means that as time goes on, that total momentum will never change. So we can measure the momentum of the entire system at one point, wait as long as we want, measure the momentum of the system again, and it will be exactly the same as the first measurement. Now the individual momentum, meaning the masses and velocities of the individual objects, they could be different, but the total, the sum of all the momenta will be the same. So that's the principle of conservation of momentum, and that's going to be the basis of a lot of the work that we do in class going forwards, because that's the basic physical principle we want to use to try to understand how the individual objects trade momentum around. Of course, we have to know they're not going to lose momentum, and that's what this principle tells us. Okay, great. So this has been a little introduction to particles and systems, talking about momentum conservation. Thank you for watching, and I'll see you in class.